Hello. In Lab 3, we will talk about applications of integration in physics. This means we will talk mostly about center of mass and work. Therefore, for the most part, nothing new is really needed here besides the theory from the class. In this examples file, we will instead focus on how to create a family of functions and how to do work directly to the family of functions. So what is a family of functions? A family of functions is just a set or a collection of functions that differ from each other by some rule or pattern. For example, let's say we have a family of function f sub n of x equals n times x times e to the negative nx squared. In this case, n is what's called a parameter, and so for each different value of n, we will have a different functions. So f sub 1 of x will be x times e to the negative x squared, f sub 2 of x will be 2 times x times e to the negative 2x squared, and so on. So we can define f sub 3, f sub 4, and so on. Normally, though not necessarily, the parameter will be non-negative, non-zero, integer. So 1, 2, 3, 4, and so on. To create a parameter, we will use a similar method to how we created a variable. So in this case, we're going to create a variable n, but we will give it extra conditions. So it will be an integer, it will be positive, and it will be non-zero. And now we can create our function. So f sub n equals to whatever our family is. So notice we're, in essence, treating n as the variable. And for the most part, we'll be treating n as the variable in Jupyter. We just need to remember that this is not a variable, it's a parameter. So in this case, there we go. This is our fn. This is exactly what we wanted. So let's try to see some of these functions and evaluate them. For example, let's say I want to know what f sub 2 is. So all I need to do is substitute 2 instead of n in my fn. So there we have, it's 2x e to the negative 2x squared. If let's say I want to now evaluate this at x equals 1, we'll do the same thing. We will use f2 and we will substitute there 1 for x. So this would be 2 over e to the e squared. We can do both of these substitutions at the same time. So for example, let's say I want to know what is f sub 1 of 3. So n has to be 1 and x has to be 3. So we can use a substitution here as well. And it will be 3 over e to the 9. And be very careful with all of these brackets and parentheses. Of course, often it will be useful to also use n function so we can see what this is equals to in a decimal form. And there we have it. We can also find, let's say, limits of a family of functions. So let's say we want to know what happens to f of x as x goes to infinity and n goes to infinity. Well, we can do this separately. So I can find, let's say, what's f sub 1 goes to as x goes to infinity. That would be 0. Then what is f sub 2 goes to as x goes to infinity? 0 as well. Same thing for f sub 3. So we can kind of see, oh, there is a pattern 0, 0, 0, so most likely the whole thing approaches to 0. But we can do this better. We can take this limit of the whole family, fn. So we don't substitute anything here. This is just f sub n. And we make x goes to infinity. And we can see it is, in fact, 0. Our second example will focus on plotting. Suppose we want to plot the first 6 functions in our family. So from f sub 1 to f sub 6. Now there are multiple ways of doing this. One way is to just plot each of them separately. So write a whole code for each function separately and plot it. Now this is very time consuming and not very efficient. Another way to do this is to plot all 6 functions on the same graph, which is much faster. However, it's a lot messier because now we need to be able to distinguish between 6 different graphs on the same graph. So we will use another method. And that's when we try to plot all 6 functions as a separate graphs in the same figure. To do that, we will use a subplot command that you may have seen in the tutorial file. So before we plot, we will also need to lambdify our functions. Remember, we created the whole family using SymPy. Therefore, we need to lambdify it back to NumPy so that we can plot it. And you can lambdify each function separately. This is pretty much the same thing you've done before. Or we can actually lambdify the whole family at once. So main thing here is that instead of just a variable, I'm going to have a list of variables, so n comma x, and that's it. So let's lambdify our function. So for example, now I can say f and n 2 comma 1. So this means f sub 2 evaluated at 1. Or I can say f and n 3 comma 0.5. So that's f sub 3 evaluated at 0.5, and so on. Okay, so now let's plot. So we will create our figure file. We will have to use a subplots command. So that's our figure. And since we're going to have 6 different graphs on this figure, each of them will have its own axes. And so we have to create 6 axes. We're going to denote them with AX1, AX2, and so on up to AX3. We will also group them so that we have 3 in one group and 3 in the other group. Each group is a row. So we have 2 rows, and in each row we will have 3 different axes. We will also specify that here. So we have 2 rows and 3 columns. We will add few extra conditions here. So share x is true and share y is true. And this means that all 6 graphs will have exactly the same x-axis and exactly the same y-axis. Okay, after that, it's more or less the same thing. We will have our x values, so from 0 to 2. So this graph will be from 0 to 2. And then we create each graph separately. So our first graph, AX1, here we will plot f sub 1. We will also fill the area between the graph and the x-axis. So to do that, we will use fill between. So it will be whatever my values are for x, which is from 0 to 2. And then it will go from x-axis all the way to values of my function f sub 1. Then we add the grid and we'll give it a title. And we will do this for each graph separately. So here's second one, so AX2, we will plot f sub 2, we will fill the area, and so on, so on, so on. We will do it 6 times for each of them, and then we will draw a picture. So there we have it. Our 6 graphs, F1, F2, F3, and so on. Each axis go from 0 to 2. Notice all the y values are exactly the same, the scale of the y-axis. And we also fill the area underneath the graph. If, for example, you don't want to fill the whole area underneath the graph, but for example, you want to fill only between 0 and a 1, then you can create a new range for your values for x, so separate one, and use it here in a fill between. So for example, I would have to say something like, let's say x2 values to be linspace from 0 to 1, and then here instead of using xval, I'll use the x2 values. Now, you may think that this is not very efficient because in essence, I use the same 4 lines of code 6 times in a row. So maybe there's a way to just do this once and then maybe loop around over all of my axes. And we can do that as well. So here's another piece of code. This is exactly the same as this whole set, except I'm put my drawing in a for loop. So I only have to do this once. So let's see what we have here. The first thing is I define my subplots. So this part is exactly the same as before. So I have 2 rows, 3 columns. I'll share my axis and so on. Notice I will no longer specify how exactly my axes are arranged. I don't really need that. I don't need to give them separate names anymore. Then here's my for loop. So for I and x in enumerate axis.flat. So enumerate in essence, will go through all of my axes, but the numerator can only go through lists. Now, this axis here is not a list. It's actually an array. It's a 2 by 3 array. I have 2 rows, 3 columns. So I need to use this dot flat to, in essence, flatten it and create a list. So now first row will be the first 3 entries of my list, and then the second row will be the second 3 entries of my list. And I will, well, enumerate. So this is just an index. It will go 0, 1, 2, 3, and so on. So first axis will have I equals 0. Second axis will have I equals 1, and so on. And now for each of those axes in axis, I will plot, I will fill the area in between, and so on. I will also write a title. There are 2 things to point out here. Notice I have to use I plus 1 in each case, since my first axis should be called f sub 1, for example, but I is 0, so it's always going to be 1 lower. So if I add 1, I get the correct numbering. And also in my title text, my actual title will be f sub something here, $I. This $I means that I will replace this part with some kind of integer. That's what I stands for. And then I'll specify what exactly I'm replacing it with. So I will replace it with the I plus 1. So again, it's going to be f sub 1, f sub 2, and so on. So let's see what it looks like. As you can see, it looks exactly the same as the previous graph. So this is a way more efficient way of doing this. This, of course, is not always useful. For example, maybe I don't have a nice clear pattern to which families I want to plot. For example, let's say I want to plot f sub 1, f sub 10, and f sub 15. So I can create a list that contains 1, 10, and 15, and maybe do it that way, or I can just do those 3 graphs separately. So it depends what you have. You have to decide on your own which method is more efficient for you. In our next 2 examples, we will look at how to integrate the family of functions and how to differentiate family of functions. So in example 3, we'll talk about integration. So let's say here we want to know the area, this blue area underneath the graph. So I will need to integrate f sub 1, f sub 2 between 0 and 2. We can do this separately. So for example, here I am integrating f sub 1 between 0 and 2. So the area here will be 0.49 and so on. I can do this the same thing for f sub 2. I can do the same thing for f sub 3. So we can look at these values. We can see that our areas more or less approach 0.5 probably. It's getting 4, 9, 9, 9, 9, 9, and so on. So maybe let's try to find if this is true. We can integrate fn between 0 and 2. So we don't specify what n is. We just take all of them at once, and we're integrating all of them at once. So this should give me some kind of expression in terms of n. And we do. So it's 1/2 minus e to the negative 4n over 2. And now that I know that, we can take a limit. So what happens as n approaches to infinity? So we'll take a limit of this area as n approach infinity. And we indeed get 1/2. And by the way, this can be quite more complicated if n is not an integer. But since n was an integer, usually these type of calculations are quite simple. In our 4th example, we'll do something very similar, but with the differentiation. So now let's say I want to know where is my maximum here and what happens to it as n gets larger and larger and larger. Okay, so we'll find the derivative. So it's a derivative of all of the fn's together. That's what it equals to. We will now use solve set to figure out when the derivative is equal to 0. We can see we got 2 values. And since we only care what happens between 0 and 2, well, I only need the positive one. This is clearly a negative value. This is positive. So this is the critical point I care about. So let's define critical point of sub n. to equal to that value. And then let's also find a critical value. So just evaluate your function f sub n at that critical point. So there we have it. So let's see. So what's the maximum of the first few functions? Well, we see that a maximum of f sub 1 is at about 0.7, 0.42. A maximum of f sub 2 is at about 1 half and 0.6. And maximum of f sub 3 is at about 0.4 and 0.7. So we can see that x coordinates are getting lower and the y coordinates are getting larger. But it doesn't really give us a good way to determine the pattern or see what happens if we take a limit, for example. So let's actually take a limit then, specifically. So let's say we'll take a limit of all of these critical L as n goes to infinity, and we'll take a limit of all the critical values as n goes to infinity, and print them out. So we see that as n gets larger, the coordinate of the extrema goes to 0, infinity. So that means if we go back to the pictures, this maximum getting closer and closer and closer to the y-axis, but it gets higher and higher and higher and higher without bound. And that's it. In this lab 3, you will have 3 problems. The first problem will be a modeling problem dealing with work. So for the most part, you need to recall how to deal with models, how to create them, and how to deal with polynomial library. In the second problem, you will have to deal with center of mass. This is quite an involved problem, but for the most part, there is nothing new there. And finally, in the third problem, again, you will have to deal with the center of mass, but this time with the given family of functions. So this is the problem where you have to use this example file to create the family of functions, to plot them, and so on.